Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-3 lesson on the Rational Roots Theorem. In this one, we are going to find zeros of polynomials using the RRT. For your warm-up, let's say that one of the roots of this polynomial below is x equals 8. We're giving you that one. Based off of that, see if you can find the other roots. As a hint, synthetic division might be helpful here. All right, let's see if you figured out what you needed to do here. So if they give you one of the roots, why not just plug it in with synthetic division? Let's see what happens. So we've got coefficients of 1, -5, -34, and 80, and the box number will be the root that they just gave you. So we'll plug 8 in here, bring down that first one, times 8 gives us 8, plus -5 gives us 3, times 8 gives us 24, plus -34 is -10, times 8 is -80, plus 80 is 0. Now this shouldn't come as a big surprise. You should get a remainder of 0. I mean, they told you 8 was one of the roots. That means when you plug it in here, you get 0, and plugging in 8 and getting 0 is the same as dividing by x minus 8 and getting 0. The cool thing about this, though, is that we can now, since this 8 gave us a remainder of 0 and we have a factor of the polynomial, we can actually factor the polynomial into x minus the root times the quotient. So we can split this up into x minus 8, because again, if plugging in 8 gave us a remainder of 0, that means x minus 8 is a factor. And then the other factor is the quotient, x squared plus 3x minus 10. At this point, since they wanted us to find the other roots, we're just going to break down this quotient here. So just solve the quotient for the remaining roots. Now the nice thing here is that we know everything about solving quadratics. We could factor, we could use quadratic formula, whatever's going to work. This one is factorable. Two things that multiply to -10 and add up to 3, that would be -2 and +5. And then if we just go through and zero out each of these, we have 8, which they already told us in the beginning, 2 from this factor, and -5 from this last factor. So that's pretty neat. If you already have one of the roots, you can use synthetic division to help break it down and get the other roots. But what if they don't give us that first root? What then? To find that first 0, we have to do a process of guess and check. In order to narrow the number of numbers that we're guessing and checking, watch the following to see if we can pick up a pattern here. So here's a polynomial I'm going to give you, 9x cubed plus 15x squared minus 8x minus 4. And I'm going to give you its factorization too. Don't say I didn't give you anything. So I'm telling you it's 1x plus 2, 3x minus 2, and 3x plus 1. If you wanted to, you could multiply this out and verify it. What I would like to draw your attention to, though, is take a look at the constants in each of these factors. So +2, -2, and +1. Now, what do you notice about these factors, these constants anyway, versus the original polynomial? Well, you might have noticed that if you eventually multiply all these out, you'll have to multiply the 2, the -2, and 1 to get this -4. To state it another way, these constants are all factors of the constant in the polynomial. The factor constants are factors of the p of x constant. Okay, well that's kind of neat, but it doesn't get us much at this point, so let's keep going. Let's take this polynomial again, and the factorization again, and this time I would like to direct your attention to the linear terms in each of those factors. So 1, 3, and 3, the coefficients of those linear terms. What relationship do you see with these numbers versus the original polynomial? Oh yeah, 1, 3, and 3, that multiplies to give us this 9, which makes sense because if you multiplied all these together, eventually you'd be multiplying 1x, 3x, and 3x together to get 9x cubed. So then these numbers, the x coefficients, are all factors of p of x's lead coefficient. Let's do one more little experiment here, and let's find the zeros of this polynomial. So going through here, we've got -2, 2 over 3, and 1 over -3. So what pattern do we see here? Well, if we think of these all as fractions, the top number of the fraction, the numerators, those are what you got by adding or subtracting those constants from each factor. And the denominators of all these fractions, well, that's what you got when you divided by the coefficient of x in all of these. So that means that the numerators are factors of the constant in the original polynomial, and all of these denominators in your roots are going to be factors of the lead coefficient. This is essentially what the rational roots theorem says. The rational roots theorem says if a polynomial has rational roots, then those roots will be plus or minus factors of the constant divided by factors of the lead coefficient. So where this comes in handy is we can use this to generate a list of possible rational roots, or the PRR list for a polynomial. So for example, if I'm making one of these PRR lists for the polynomial I gave you up top, we have factors of 4 over factors of 9. Those are going to be our possible rational roots. Well, what are the factors of 4? That would be 1, 2, and 3. Factors of 9, that would be 1, 3, and 9. And then taking a look at the different combinations I can generate, let's say I divide all of these by 1. So that gives me the possible factors, or the possible roots of 1, 2, and 4. Okay, well, let's say I divide all of these by 3 now. Now I've got 1/3, 2/3, and 4/3. And finally, I could divide all of these by 9, so that's 1/9, 2/9, and 4/9. This is a long list. The important thing to realize here is if you look at my actual roots, -2, that's on the list, 2/3, also on the list, and -1/3, since this is plus or minus, that was also on the list. So if there are rational roots, they really will be on this list that you generate. So if you're looking for those kinds of roots, these are the only numbers you will ever have to guess and check on. It's still a lot, but at least it's less than infinity, right? The only catch here is that this only works for rational roots. It's not going to work for irrational roots like square root of 2 or imaginary roots like 2i. You'll have to get those roots through another method, but this might at least get you started. Now that we've seen what the rational roots theorem does, let's use it to help us solve this equation here. So they're not giving us any of the roots for this cubic polynomial, but that's okay. We can generate a list of possible rational roots. Pause the video and see if you can generate the PRR list for this. All right, let's see how you did. So again, we need factors of the constant, which is 50 in this case, divided by the lead coefficient factors, which is just the lead coefficient is 1, so that's going to be easy. Factors of 50, we've got 1 and 50, 2 and 25, and then 5 and 10. I usually figure them out in pairs. And then factors of 1 is just 1. If we want to convert our PRR list into something that's not in this weird fraction form, well, that's going to be easy here. We're just dividing all of these by 1. So here's our list of possible rational roots. Now, once we have this, what do we actually do with it? Well, I said this was a guess and check process. So you essentially have to plug all of these PRRs into your function until you get 0. Now, you could do this in a variety of ways. If you don't have a calculator, you could use synthetic division for this. But if you do have a calculator, there's a much faster way to do this. So we're going to start this process, and I'll show this to you, by entering your polynomial into the y equals. So let's do that now. So here I am in this y equals button here. I've entered my polynomial in y1, and now that I've done that, I'm going to start plugging things into it. Now there's a lot of ways to do this. The fanciest way to do this, I think, is if you go to table set and set independent to ask. Let me show you that. So back on the calculator, if you do second window, that'll bring you to the table set menu. And among other things, there's this independent thing that's auto versus ask. This is basically saying, do you want it to generate the x values automatically, or do you want them to ask you for the x values and then they'll give you the y values back? We want them to ask us for the x values when we call up a table for this, because we have very specific x values here that we want to plug in. We don't want to be at the mercy of whatever the table feels like showing us. So after you've done that, go to the actual table and then just start entering these x values. Check this out. So here I am back on the calculator. I'm going to do second graph to get my table. And this x column is blank because it's waiting for us to give it the x values to test out. So I'm going to start at 1 and then just do positive, negative, and work my way down this list. So plugging in 1, press enter. That gives me an output of 54. That's no good. Let's do negative 1 now. That gives me 34. Still no good. Let's try 2. 52. Oh, that's so not good. How about negative 2? Oh, that gets me a 0. All right. So this is what we just did on the calculator here. Well, once we've found one of the zeros, we're going to do essentially what we did in the warm-up and plug that into the polynomial using synthetic division. Now again, why are we bothering to do this when we know we're going to get a remainder of 0? We're not really interested in the remainder. We're interested in the quotient because we're going to start factoring this thing into the quotient times whatever factor this negative 2 generates. So let's start with our coefficients. We've got 1, negative 6, 9, and 50. And I'll let you pause the video and see if you can go the rest of the way and factor this using synthetic division. All right, so our box number is going to be that negative 2 that we just found was our 0. Bringing down that 1, we multiply by negative 2. That's negative 2 up here. Plus negative 6 is negative 8. Times negative 2 is 16. Plus 9 is 25. Times negative 2 is negative 50, which of course gives us 0. So we have the factor x minus negative 2, or x plus 2, and x squared minus 8x plus 25. Is this factorable? Well, let's see. We've got numbers that multiply to 25 and add up to negative 8. Well, the only things that multiply to give me 25 are 1, 25, and 5, and none of that is going to give me negative 8. So at this point, hopefully you recalled the quadratic formula. Here it is if you didn't. That's negative b plus or minus the square root of b squared minus 4ac all over 2a. We're going to use the quadratic formula now. This is kind of the last resort when you can't factor, but it does have its uses. So we're going to have negative 8 plus or minus square root of negative 8 squared minus 4 times the a value of 1 times the c value of 25 all over 2 times the a value 1. All right, let's crunch these numbers. So that's going to be positive 8 out there. Inside, we've got 64 minus 100. That comes out to negative 36, and we have 2 in the denominator. Square root of negative 36, well, now we're getting into imaginary number land. If you take out an I in square root positive 36, that's 8 plus or minus 6i over 2, which we can reduce to, let's see, 4 plus or minus 3i. So our answers for this then, we found that negative 2 was our only real root, and then we had the imaginary roots, the complex roots, of 4 plus or minus 3i. Here's another one for you to try out. Pause the video and see how far you can get. All right, so let's start with that PRR list. We have factors of 9 over factors of 2. So that's 1, 3, and 9 on the top, and 1 and 2 on the bottom. So we have 1, 3, and 9 over 1, which is just themselves. And then 1, 3, and 9 over 2, so 1 half, 3 halves, 9 halves. So this is only 12 numbers we'll have to plug in with the calculator potentially. Let's put our polynomial in the y1. So there we go, we've done that. And now I'm going to start testing these numbers in my table. So if we go back to table, and it's still on ask from before, we still have these values from the last problem. Now, I was going to test 1 and negative 1 anyway. You actually always end up testing those, and sometimes you get lucky and it is one of those. We didn't want to test 2 and negative 2, though. We wanted to test 3 and negative 3. So I'm just going to delete these 2 entries, and now I'll put 3 in there instead. And, oh, hey, right on the first shot. Not bad. So that means 3 is a 0. So we're going to plug 3 in now using synthetic division. So we've got coefficients of 2, negative 7, 9, negative 21, and 9 again. Box number of 3. Bring down that 2. Times 3 is 6. Plus negative 7 is negative 1. Times 3 is negative 3. Plus 9 is 6. Times 3 is 18. Plus negative 21 is negative 3. Times 3 is negative 9, and of course, plus 9 is 0. So we have the factor x minus 3, and then we have 2x cubed minus x squared plus 6x minus 3. Okay, so what now? So you might notice that this can be factored with grouping, but let's pretend we don't notice that. And it won't always be factorable by grouping. So in this case, we can keep going. Okay, so how do we keep this rational roots process going? One thing you should definitely do is revise your possible rational roots list using the quotient. We no longer have to use the old list because this quotient has a smaller constant in it now. Now we're looking at factors of 3, which is just 1 and 3, divided by factors of 2, which is just 1 and 2. So this is going to generate a smaller list. We've got 1 and 3 over 1, which is just 1 and 3, but now the only other ones are 1 over 2 and 3 over 2. Okay, so you've got this list. What do we do with it? You're no longer going to test these numbers in the original function, right? Because if you do that, 3 is going to give you 0 again because it gave you 0 the first time you tested it in the original. Instead, you now have to test your PRR numbers in the quotient, q of x here, this 2x cubed minus x squared plus 6x minus 3. I recommend that you put this in y2 in your y equals, which I'm going to do now. So I'm back on my calculator. I'm going to y equals, and now in y2, let me do 2x cubed, and we've got minus x squared plus 6x minus 3. Okay, let me go to my table again. And now we're going to be looking in this y2 column here, right here. So when you're doing this, do you have to test bad roots again? Do you have to test good roots again? So the bad roots, if the ones that didn't work the first time in your expression that had more factors, are not going to work when you try them on something with even less factors. So the nice thing is you don't have to test bad roots twice. That doesn't really save you a ton of time on the calculator if you've already got them in this original column here. But if you had to do this by hand using synthetic division, it would save you time not to test the bad roots again. How about the good roots? You do need to test good roots twice. Just because they work the first time doesn't mean they'll never work again. This 3 here might have been also a factor of this smaller polynomial. Now, if we look in the table here, plugging 3 into our quotient did not give us 0. So the good root did not work twice. But we still have to check. So let's check a few more. Going back to my calculator now, let me try out negative 3. That doesn't work in the quotient. Again, we're just checking the y2 column. And what's on my list after that? Well, positive 1/2. Let's try that. So you can enter this as a decimal, or you can just do 1 divided by 2 and let the calculator figure it out. That's a much better way, for example, when you have something like 1/3. But now this 1/2 comes out to 0, so this is good news. This means we can do synthetic division on the quotient now using 1/2. So we've got coefficients of 2, -1, 6, and -3, a box number of positive 0.5 or positive 1/2. So bringing down the 2, multiply that by 1/2, that's just 1, plus -1 is 0, times 1/2 is still 0, plus 6 is 6, times half is 3, and that gives us the 0 that we were expecting in the end. So just to remind you here, we've got x minus 3, that's the original factor that we took out. We also now have a new factor of x minus 1/2, and we have the quotient 2x squared plus 6. So let's go ahead and solve this last one now. No need to use the quadratic formula. You can just subtract 6, divide by 2, and then if you square root both sides, we just get plus or minus I radical 3. So summing up, we've got 3, 1/2, and plus or minus I root 3 for our answers on this one. Now again, on this one, we could have used grouping, and it would have been a lot faster than doing all this. So always check before you use Rational Roots Theorem again to see if grouping will work. As a wrap-up here, to solve the following polynomial, let's say Polly, that's a nice name, came up with a list of possible zeros, which she gave here below. Which 4 numbers in her list cannot possibly be solutions? Pause the video and see if you can pick the bad ones out of the lineup here. All right, so the key to doing this was coming up with, your guide for what the possible rational roots could be. We should have factors of the constant, 10, over factors of the lead coefficient, 12. We don't have to list out all the factors of 10 and 12 to do this. We just need to go through the list and see which things in the numerator are not factors of 10 and possibly which things in the denominator are not factors of 12. So going through our list, 3 is the first problem. That's not a factor of 10. Neither is 4. 12 also is suspect. And 6 over here, 6 over 1, that's not going to work either. Are there any things now that we can rule out with the denominator of 12? Let's see, 12, that's okay. 4, that's okay. 10, that was already gone because of the 3. 3, 2, 3, those are all fine. 5, but that was already ruled out with the 4 in the numerator. 6 is okay. 1 is fine. 3, 1. 5 is no good, but 12 was already ruled out by the numerator. And that's it. Everything else would have worked. So at the end, we just have 3/10, 4/5, 12/5, and 6. And that's all the time we have. Until next time, this is Mr. Sutton signing off.